Alright, so today we discuss a problem on binary number, and the name of the problem is the parity of a binary word. So the statement is very simple. So we have a binary word, have a binary number. We want to find its parity. So what is parity? Parity is essentially a property of a binary number. So we say that a binary number has a parity of 1 if it has an odd number of ones in it. And likewise, the binary number would have a parity of 0 if it has an even number of ones. So as an example, so if this binary number has 3 ones, 1, 2, 3, then it would have an odd number of ones. So this corresponds to a parity of 1. And this binary number has 2 ones in it, and this corresponds to 0 because it has an even number of ones. Okay, the problem statement is very simple. So this problem essentially tests the understanding and whether we could manipulate binary operators, and we could deal with properties of binary numbers. And so we first go through a brute force solution like we should with our algorithmic problems. We try to use a brute force solutions, and then we can see that whether we could use some methodology to optimize it. So the brute force solution, the code goes like this. So first we want to go through the code. So essentially we start with the result, and we enter a loop. Note that for the edge case, when the input is 0, then we simply return 0. And this is correct because the number 0 has no ones in it. And so it has 0 ones in it. The number 0 number 0 is an even number. Therefore, this binary number has a parity of 0. And we return 0 in this case, which is correct. So if x is something else than 0, if it has an arbitrary many ones in the binary number, we enter the loop. So this essentially is the key step. We see that there is an AND operator and an XOR operator. So this is the XOR operator. And if you, just as a reminder, if you're not familiar with the XOR operator, essentially this operator gives true, returns value of 1 only if two sides have different values. So in these two cases, it would return a value of 1. Otherwise, it would return a value of 0. Okay. So in this algorithm, this step happens first. So first we AND the input with 1, and then we XOR it with the result, and then we store the result of the XOR with the result back into the result. Okay, it's a little confusing, but we can go through a detailed example to help you see the underlying mechanism of it. So first step is we AND the input with 1. What this does is it tests the last digit of the input against 1. So if the input, so we see that x, if just as an example, this is the original x. So we first AND x with 1. And we could just place placeholders in front of 1 or we just put 0 as placeholders in front of 1. And we can see that everything that AND with 0 would give us 0. Right, so essentially we don't have to look at anything in front of the ones, in front of the last digit. We don't look at any of these. We only look at the last digit. So every time we go through this step, we only look at the last digit of the binary number, right? So and this step would only return a 1 if the last digit is a 1, because in this case, last digit is a 0, and this would return a 0. So x and 1 would give us, which is a 0, okay? And we're going to XOR this 0 with the current result. Current result is 0 because it is initialized to be 0. 0, so result XOR with 0 would give us 0, right? Because X will only give us 1 if these two are different. Result is 0, and the right-hand side is also 0, so it will give us 0. So, wait. Yeah. And what does this mean? So it means that at current position, we have only examined the last digit of the input. The last digit is 0. And at this step, we didn't see any ones, and which is kind of trivial because if we didn't see any ones, then it has an even number, namely 0 number of ones. 0 is an even number, so it has a parity of 0. Okay, and the more interesting case is when we right shift the input by 1. Right shift by 1 would mean that we get rid of the last digit of the input, and then we shift every digit to the right by 1. So this would give us, so we get rid of the last digit, here, and then everything is shifted to the right by 1, and this is just a placeholder. And now we can see that we get rid of the digit that we already have tested against. Then we move on to the next digit, and the next digit is going to be 1. So as we know that this step only tests the last digit of the input with 1. So 1 and 1 would give us 1. And current result is 0. So result XOR with 1, 0 XOR with 1 would give us 1, right? Because these two are different. So currently result is 1. And this means that when we encounter the first one, and at this point we have only seen 1. This means that it's at this point the binary number has an odd number of 1s. The parity is 1 in this case. And then we go on to see that the last digit we want to test against after the right shift is 0, right? After the right shift again will give us 0 as the last digit. And we have already seen it that the last digit would give the value of 0 in the end step here. And then the current result XOR with 0 is 1. XOR with 0 would give us 1 because these two are different. So we see that the result wouldn't change upon encountering a 0. Because if the result is a 1, it's not going to change upon encountering a 0. It only changes when we encounter a 1. So this brings to the key point of this brute-force solution is the usage of the XOR operator. In this case, the XOR acts as a switch. So when we see a 0, it tells me to stay, like don't flip on the switch. But when we see a 1, we flip the switch. So it's flipping on or off. We just flip the switch, right? So every time we encounter a 1, we flip the switch. The first time we encounter a 1, the result is flipped to 1, which indicates that we see the first one in the binary number. 1 corresponds to odd number, so we have a parity of 1. The second time it flips to 0 because we see 2 ones. 2 is an even number. So the parity is 0. So in the brute force solution, we always have to remember that XOR acts as a switch, and the switch flips on and off when we encounter a 1 in the binary number. Okay? And we also want to analyze the runtime. So since this is a brute force solution, the runtime, it essentially goes through every digit of the binary number. So the runtime is going to be n, and n is the number of digits in the number. Okay, and brute force is, I mean, big O of n is not bad, but when we can find a much better solution, we always want to aim for the much better solution. And we will see here, an improvement to the algorithm that the brute force algorithm we just discussed. And we will not go into the technical details of this revision, but we will just state the method we're going to use, state the procedure of the algorithm, and we will see an implementation of the algorithm. So the idea in this improvement is based on some properties of parity and the properties of the XOR operator. So keep in mind that we're just skipping over some details here, but we're just applying some properties of parity and the XOR operator in order for us, in order that we could say this, we could apply this algorithm, and we could do it this way. So this approach is essentially a divide and conquer approach. And we will see a lot of divide and conquer problems. And in these problems where we can use this method, we tend to be able to reduce the time complexity by a lot, as we will see with this algorithm. Okay, so we will see an example first. We'll just walk through the algorithm, and we will see how to implement this algorithm in Python. So we want to compute, say, 8-bit number. I'm sorry, 8-bit number. So suppose we want to calculate the parity of this number. And what we could do is we could split this number up in the middle, and we could compute the XOR of the first half and the second half. So we want to do XOR of these two numbers, and what we can see is we have 1, 0, 1, 0. So remember, the XOR only gives 1 if the two digits are different, right? And now we have 1, 0, 1, 0, right? And then we compute the XOR again of the first half and the second half. So we would have 1, 0 XORed with 1, 0, and this gives us 0, 0, right? So, and then we again compute the parity of 0, XOR of 0 and 0, which gives us 0. So then we could conclude that the parity of 1, 1, 0, 1, 0, 1, 1, 1 is 0. So we can see here that you can count that we have 1, 1, 2, 3, 4, 5, 6. We have 6 ones. Since it's an even number, we only have 6. We have a parity of 0. Okay, and we now see we now try to see the time complexity of this. So every time, so we are only comparing, we're only going through the steps. So we're dividing up the number every time. So when we see something like this, we note that the complexity is going to be the log base 2 of n, and we usually just write it as log n, right? It does not matter. So this approach essentially, each step of the approach will reduce the input size by 2, and this allows us to use log. And in general, log is probably the one of the most optimal options that you can get, and because the log curve grows really, really slowly, like this. So as the input size increase, the log only increase by a tiny amount. So essentially, this is very, very fast. Okay, so we now see an implementation of the algorithm described above. So notice that every step we have kind of this number decreased by 2, and this is kind of a sign that we are using the divide and conquer. We are reducing the input size by 2 every single time. And so the first step we're trying to do here is we're shifting the input 32 bits to the right. So what this does is, if we have a 64-bit number, then after this operation, what it returns is um, is a number that has the first 32 bits of x in the rightmost 32 bits. So this returns a number where, say, okay, so say this is the binary number, and each b represents the 1 or a 0, so like each place in the binary number. And after this operation, what we have is, and everything here is filled with 0. Okay, so it shifts the whole number to the right by 32. So it puts the first 32 bits of the original input onto the last 32 bits. And if we XOR it with the original 64-bit number, so we just represent it like this. So essentially we just copy it here, and B32, we're essentially doing the same thing here, B31 and B1. Right, so XOR with this. Notice that we're ignoring the first part. We don't look at it, but we only look at this part, and this part usually is what this algorithm describes. Right, we are XORing the first half with the second half. This is the first half. This is the second half. We are XORing it. So, and at this time we're storing this result. We're storing the whole result back into the X. But at the end here, we are only extracting out the last digit of the of X. So we're ignoring everything in front of here, on the last step, so that we could get what the parity is according to this algorithm. And we move on, and we see that this step is essentially the same. We are only looking at, we're moving the current X. Current X is current X refers to this step here, and we are only looking at the last 32 bits. So we're dividing up the 32 bits into 2/16, and then we are XORing them again, like this step here. Except that the input size is larger in this case. And then at the end, we are comparing X shifted 1 is what this step is, and we're XORing it is is the same as the step in the example. and then we're extracting out the last digit to be the parity. Okay, so just a couple of things to note here. In this case, we're kind of assuming that we have a 64-bit number. And this means that we could just list this out and you could say that it is constant time. But if we have some number that is bigger than 64 bits, then we would have to run a loop. And if we have a loop, we would have to analyze with an indefinite, with an unknown input size n. And then the loop would run log n log 2. Loop would run log 2n number of times. And this is where the log 2, this is where the big O of log n comes from. Okay. And another thing to note is if a binary number is not a power of 2, if it doesn't have a power of 2, then we would still be able to do it because we just fill up. Say if a number is 11011 and we want it to be a power of 2, then we could just fill this up with zeros in front of it, and this would still ensure that we get the right results. And you can try this out with this example. You can see that we're still ensured with the right parity result. So this is one of the best solutions that you can have with this problem because it's log n, and most of the time the more optimal solution to log n is constant time, which is sometimes it's just not possible to have. So this is one of the best solutions that you can get with this problem.